Okay, so why don't we get started? So I'll continue from where we left off last time, but couple of announcements first. I sent out an email indicating that there was a quiz I had put up on the Moodle site. It's going to time out by end of today. If you haven't yet taken the quiz, please do. And for those of who are not here, if you see them, just let them know. Okay, they should have gotten the email, but just in case. Right? So every week, we will have a quiz out on Friday. We'll time out by Monday morning. Today I left it open through end of the day just so that I could announce this in class one last time. Okay, so that's one. Second announcement was I just wanted all of you to know who the TA is. It's Pratik is actually sitting right here. So just so that you can associate a name with a face, he is going to be responsible by and large for helping out with the lab part of the class. So you will probably have a lot of discussions with him and talk to him on a frequent basis. So just keep that in mind. We do not yet have office hours posted for Pratik yet, but I will get that set up later today. I will have that posted on the course webpage and announce it on Wednesday. Okay. So, so what we are going to do today, so that's the end of the announcement. So I'm going to start this sort of from where we left off last time. So today's class, we are going to talk about architectural issues for distributed systems. We'll talk about different types of distributed systems. We'll talk about different flavors for building distributed systems and whatnot. But before we do that, there are a couple of overflow slides from last time that I just want to finish. Those that topic had to do with architectural issues for designing operating systems rather than distributed systems in general. Okay? So if you remember where we left off last time was I was just doing a quick recap of Uniprocessor operating system as a stepping stone to distributed operating system, and I had said that you could build uniprocessor operating systems either using a monolithic architecture where the entire kernel is implemented as one entity and it runs as one privileged process when the machine boots up, or you could have at the other end of the spectrum microkernel architecture where your operating system kernel is essentially a bare bones kernel that is responsible for tasks such as security and inter-process communication, and lot of the functionality that you normally put in the kernel are implemented as user level processes, as system processes that collaborate to implement operating system functionality. Okay, so in many cases when you have to perform some system call or perform some OS task, there'll often be interactions between these OS level components that are actually running as user space processes. Okay. Now, as I said, the advantage of this approach is it gives you more modularity, it gives you better security because if there are, let's say, bugs in one component of the kernel, they're isolated to that one user process and not to, and you cannot actually taint some other user processes that belong to the kernel. So better security, but there is a performance downside, okay, as I had mentioned. So do people have a sense of why there is a performance downside to microkernels?
Message passing between the
Okay, so there is going to be more message passing, okay, in the form of messages. So in a monolithic kernel, components can interact with one another by simply invoking function calls. Okay, memory manager can interact with some other component by invoking a function in that other component. Function calls are cheap. In this case, the OS functionality is split across processes. So what were function calls in a monolithic architecture become messages that go back and forth between processes in the microkernel architecture. That's going to be a significant performance hit because sending a message involves going through the microkernel, having the message appear at the other end, it gets processed, then you send back a reply and whatnot. Okay? Much slower than making a function call. Okay, so there's going to be, as a result, a performance penalty associated with microkernels. Okay, so I'm going to leave it at that. There is going to be some additional readings I'm going to put up on the advantages that I just mentioned and some of the disadvantages. So that's going to be sort of extra work that goes beyond what I discussed here. Instead, what I'm going to talk about are distributed operating systems. Okay. So essentially, a distributed OS is going to manage resources across machines, okay, not just a single machine. A uniprocessor operating system manages hardware resources on a single machine. A distributed OS manages resources across multiple machines. Okay? And there are different levels of transparency that a distributed OS can provide to its end user. Okay? At one end of the spectrum, you have what is called a pure distributed OS kernel, where the presence of multiple machines is itself transparent to end user. Okay? So it works seamlessly like a centralized OS. Okay? Operates on multiple independent CPUs, but the fact that there are multiple machines is hidden from the users. Users can just execute jobs or start up applications. So it's OS's responsibility to figure out where they run, how they run, and so on. Okay, the presence of multiple machines is going to be hidden. So there are lots of transparency dimensions here. You get location transparency, migration transparency, concurrency transparency, and so on. And there's a picture that I'm going to show you that actually is going to make this clear. Okay, so here is an example of a distributed operating system where you have these three machines, A, B, and C. There are basically kernels running on each of them that are part of the distributed OS. There is this layer that runs on top that basically then hides the presence of multiple machines from application. So all of the applications that are running on this cluster of three machines is not going to see the presence of multiple machines. And so you just submit jobs, you can essentially see all the CPUs across machines. The fact that some are local, some are remote is all hidden from the end user. Okay? That's an example of a distributed operating system, one example. Okay? And this one here, what is shown here, is implemented by a flavor of Linux and cluster-based services called Mosix, okay? Which implements what is also called a single system image, which is going to hide the presence of multiple machines. Okay? So that's one end of the spectrum. Okay? But there are different dimensions to distributed operating systems, and we will see, depending on the coupling between the OS and the machines, you will get different flavors. Okay? So you have distributed operating systems where you hide and manage hardware resources, the multiple machines. You will have what is called a network operating system. Network operating system actually is going to provide less transparency than a distributed OS. Okay? Most operating systems that you deal with today are actually network operating systems, which means they will provide you network services for one machine to access resources on other machine, communicate with entities on other machines. But the fact that there are multiple machines present is not going to be hidden from end users. End users will actually see multiple machines on your LAN. They have to explicitly either remote login or access resources on other machines. Right? So less transparency, but more convenience from designing the OS perspective. I shouldn't say convenience, less complexity from OS design perspective, because you don't really need to provide lots of different dimensions of transparency. Okay? And we'll see that a middleware is actually going to sit somewhere in between. It will take a network OS and make it look like a distributed OS, okay? Even if you don't have a pure distributed operating system. Okay? So somewhere between these, you also have a multiprocessor operating system, okay, which is going to generalize a uniprocessor operating system, but is not really distributed. Okay? So this is simply an OS kernel that runs on a machine that has multiple CPUs or multiple cores. Okay? Now, if you have, let's say, a laptop with 2 cores or even a phone with 2 cores, you have essentially a multiprocessor OS. Okay? The fact that there are multiple CPUs is may not be evident to you. You just run applications, applications are mapped to CPUs and so on. Okay? So that's what a multiprocessor OS will do. It is going to generalize the notion of uniprocessor operating system, because you need to provide additional functionality for the applications to run correctly on a multiprocessor system. Essentially, caching out the data has to be done in a consistent fashion and so on. We won't go into those details here. We will come back to some of these issues later. But I just mentioned this here just so that you get a view of the entire spectrum from uniprocessor operating systems to multiprocessor OSs to distributed operating system. Okay? So I already talked about the mosaics like flavors of distributed OS, where the fact that there are multiple machines is going to be hidden from the end users and end application. Okay, let's look at network operating systems. So here is a picture that shows you what a network OS looks like. Okay, so you'll see you still have these three machines. You have kernels running on three machines, and then associated with each of these kernels are OS services that support networking in some shape or form. It allows you to access resources on other machines. It provides TCP/IP support, other network protocol support, and so on. Okay. And applications will run on these machines, but they have to explicitly figure out what component runs on what machines, send messages back and forth in order for the components to communicate and so on. Okay. So if you have Windows, Linux, Mac OS, they're all network operating systems because you can run networked application on them. They don't hide the presence that there are other machines. You have to either SSH into other machines or connect specifically to other machines in order to access services. Okay? So if the presence of other remote resources is not transparent to end users, unlike a distributed OS where all of that is hidden from you. Okay? So this is basically also going to provide a lot of that functionality but less transparency than a distributed OS. Is that clear? Okay. And then, so we can use network operating systems to implement standard client server protocol. That's what this is showing here. So here is a client that runs a network OS. Here's a server machine that also runs that network OS. If you want to access data on that server machine, you have to use some sort of a file server protocol and a file distributed file system where the client has to explicitly make requests of the server and so on. So the fact that files are remote is visible to end users. Okay. Now here is a picture that shows you a middleware-based operating system. Okay, this is going to take a network OS and try to make it look like a distributed OS. The way it does this is you can take commodity network operating system, Linux, Windows, OS X, or any network OS, and then you're going to run an additional software layer on top, which we'll refer to as the middleware layer. Okay. So the middleware layer is going to take the functions exported by network operating system, add certain functions so it becomes more convenient for end application. Some of the resources that were no longer transparent in network OS may become transparent here. So for instance, if you have a middleware, you could just submit batch jobs, and it is the responsibility of the middleware to decide which machine to run it on. User will not have to explicitly SSH into a machine and run their application there, which you would have to do in the network operating system. Okay? So in this case, the middleware OS is going to provide you some functions that the OS itself is not providing to you. Okay? So now it begins to look like functions that a pure distributed OS provides, but without requiring the distributed OS to run on these machines. Okay? Is that clear what the concept of a middleware OS is? Okay. So there's a slide that compares them. I'm not going to go into that. It just shows you the differences which I've already mentioned. So I'm going to stop that here and switch to today's lecture. Okay, which I said is going to continue the architectural discussion. So we have looked at architectures for designing operating systems. Okay, we talked about distributed network OS, middleware OS. We'll try to see how similar concepts apply to designing any distributed system, not just an operating system, any application that is distributed as well. Okay, so just so that you know, this is now chapter 2 of the book. We actually finished chapter 1 already. Yeah, so you will have to make sure you keep up. Okay, so we are going to be progressing at a fair clip. So this is already a second chapter of the book that we are going to start now. Okay, so I'll talk from an architectural standpoint. When you need to design a distributed application, there are several options available to us. Right? You can use the layered approach. You can use an object-oriented approach to designing your distributed application. You can use a data-centered approach, as we'll see, or you can use event-based approaches. And then there are some more like Blackboard architectures and so on. And we'll go into each of this in a little more detail. Okay, let's start with the layered approach. Okay, the picture here shows what a layered approach to designing any software system is, including a distributed system. Okay. So in this case, you take a components of your distributed application and you map them into layers. Okay, so your distributed application is split into layers. Okay, so the way the layers interact with each other are shown in this picture. Okay. So what happens is a layer I in your system can interact with the layer above it and the layer below it. Layer I can talk to layer I plus 1 and layer I minus 1 and no other layer. Okay, so in this case, layer 2 can interact with layer 3 and layer 1, for example. Okay. So that's a restriction that your system imposes. So in some sense, layer 2 cannot directly talk to layer 4. If you need to invoke functions of layer 4, you have to make those requests through layer 3. Yeah, so basically that is your layering restriction that this architecture is going to impose on us. Okay. Now, there are many scenarios where the layer design is useful. A common place where you use layer design is to implement a network protocol stack. If you've taken an undergrad course in networking, you probably know that the way protocol stacks such as TCP/IP are built is through a layered approach. Okay, you will have a physical layer and a data link layer, a network layer, a transport layer, and so on. And each layer only talks to the layer above and the layer below. So protocol stacks are a popular, or rather layer design are a popular approach for implementing protocol stacks. And now protocol stacks by themselves are not distributed. Okay, they are implemented in OS kernels, but there are other places where the layered approach is useful as well. And one other scenario where this becomes useful is what is referred to as designing multi-tier web applications. So this is a distributed application where you have a client and the server itself is split into multiple components called tiers, and they are basically, the tiers are mapped into layers so that each tier can talk to the tier before and the tier after it. We are going to spend quite a bit of time later on this lecture talking about multi-tier web architecture. Pretty much all server-based web systems use multi-tier architecture. Okay. Any online store that you go to or any of these financial sites, they all use some multi-tier architectures of some sort. Okay, so we'll come back to this in just a little bit. Okay, and the picture actually shows that if you use the multi-tier approach, requests are actually going to propagate down the layers and responses propagate up. Okay, and we'll see how that works as well. Okay, so next architectural style that we'll look at is object-oriented approach. Okay, so this is no different from taking any object-oriented language and writing an application in that language where you have classes and objects, except that in a distributed system, objects are not all going to reside on the same machine. Okay, objects are going to be distributed across machines. Okay, if you have an object-oriented application that runs on a centralized machine, let's say you write this in Java, so your favorite object-oriented language, all of your objects reside in one machine. In fact, they will reside inside one process. Okay. In a distributed world, these objects are going to be split. So your application is partitioned into objects. Objects are distributed. So some objects may be on one machine, some other objects on another machine, and so on. And they will still interact with one another by invoking methods on objects, just as you do in any standard object-oriented framework. Okay. Except that some of these methods are going to be remote methods. They are going to be, you're going to use remote method invocations or remote procedure calls. Okay, if you've heard of that, you'll know. Otherwise, we'll come back to this in lecture 3 and 4. Okay. So this is another architecture for implementing distributed application. So you take your application, you partition it into objects, okay, and then you decide which objects reside on which machines and how they interact with one another. Okay. Now you can see that this is a generalization of the layered approach. In a layered approach, you could have basically mapped each object to a layer. Okay. Is that clear? Okay. Now why is it a generalization? Okay. But generalization is you no longer have any restrictions on which objects talk to which other object. If you had mapped it into a layered approach, each object could talk to at most two objects, the object in the layer above it and the object in the layer below it. In this case, we have relaxed that restriction. Any object can invoke method on any other objects. Okay? So in some sense, there is a similarity between the object-oriented and the layered approach, but the object-oriented approach is not going to impose some of the restrictions we had in the layered approach. Okay? Especially from which entity can communicate with which other entity. No such restrictions are going to be present here. Is that clear? Okay. So, third approach that is also popular is what is called an event bus approach. Okay. This is also sometimes referred to as a publish subscribe approach or a pub sub approach, if any of you have heard of these terms. So what happens in so this is a very different way of thinking about designing applications. Applications interact with one another through events. Okay, they don't actually make calls. So components, you still have components of your application that are distributed, and components generate events. Okay? And those events get delivered to some other components, which will then process the events, and then those will generate other events, and so on. Okay? So the way this works in a publish-subscribe paradigm is each component basically indicates when you start up what kinds of events it is interested in receiving. And that's essentially what is referred to as a subscription. You subscribe to certain kinds of events. Okay, so there are publishers and there are subscribers. Publishers are going to create events. Subscribers are the ones that are going to receive any event that they're subscribed to. Okay. So subscribers are going to, so components that are subscribers specify what kinds of events they wish to receive. When a publisher will publish the event, it will go to this entity called the event bus that's sitting in between, that is tracking who has subscribed to what kinds of events. So then you will basically decide that this is an event of type A. Is there any entity that wishes to receive any event in this class? If so, you are going to forward that event. Event could simply be a data item. Okay? Event is a general abstraction. It could simply be data. Okay, so you can basically use this to send data from one component to another. And by sending data, you can also make requests by asking other components to process that data for you. Okay, so publish subscribe is a popular way of implementing these kinds of applications. A simple example that I can provide here is that of a stock ticker application. If you have an application that is just looking at stock prices, okay, these are now there are lots and lots of companies that have stock prices. A particular user may be only interested in certain companies. Okay, so then you will basically say, I want to receive stock price for company A, B, and C. Okay, so you will tell the event bus saying, I'm only interested if there's an update to the stock price of even a company A, B, C, but not any other company. And the publishers in this case are going to be any entity that can update the stock price. Let's say it's a stock exchange application. Okay, so whenever the stock price is updated, it's going to be published. You'll come to the event bus. The event bus will see which subscribers have subscribed to an update for this company, and it's going to deliver it to those applications. Okay, so stock ticker applications are one example of publish subscribe. There are lots of them. It is just one example. Is that clear? You can also write event-based architectures for group chats and all kinds of things, or forums where you say, I'm interested in this forum, this forum, this forum, and whenever there's an update, the update gets pushed to you. Those can also be implemented using pub-sub paradigms. Okay? So that's event-based. The last one is what is referred to as a bulletin board or a blackboard architecture. Okay, this slightly different concept. We will come back to this at the very end of the course. Okay, lectures 23 or 24, we are going to come back and look at what are referred to as shared data space or blackboard architectures, also called bulletin board architecture. Okay, so what happens here is this is a very loose form of communication. Okay, the way to think about this is you can think of a bulletin board, let's say that's in the kitchen here in the CS department, where people go and post notices. Okay. So essentially in a bulletin board architecture, any component can come and post a note. Okay. And some other components can at some later time come and look for any notes of interest that have actually been posted for them. Okay. And if you find a match, you basically extract the data that's associated with the note. Okay. Now the reason this form of applications are very different is when you post your note, okay, you don't specify the recipient of the data. Okay, typically, when you all distributed application, when you send a message, there's an intended recipient. Okay, you say the client sends a message to the server, so the server sends back a reply to the client. Okay. But when you go and post a note on the bulletin board, let's say you are going to move to a different apartment and you want to sell a furniture. Okay? You'll just go and say, I have these pieces of furniture for sale. That note is not intended for anyone specific. It's intended to any broad class of users who are willing to buy any used furniture. But you haven't actually addressed that to any specific user. Okay? Same concept is true here. When an application comes and posts some note, you don't actually address it to any user. It just sits in this bulletin board called a shared data space. At some later point in time, some user may come along and look for a note of that kind. And if you find a match, then you basically take that data associated with the note and process it. Okay? This is referred to as bulletin board architecture. And now you may ask why actually have communication in this form. Why is it that you are sending messages with no particular recipient in mind? Okay, you're just simply saying, here is a message you posted to the node. At some later point, somebody comes and picks up that message. Okay, can you think of any scenarios where this may be useful? Any application scenarios? Not selling furniture or cars. Anybody have encountered bulletin board architectures? So I'll give an example of where this is actually used frequently. So these kinds of architectures are also used in what are called zero-conf or zero configuration systems. I'll give a very specific example. So let's say you walk into a new building, okay, which has its own Wi-Fi network, and you connect to a Wi-Fi network in that building. Okay? And you will, let's say you want to print some document in that building. You just go to a friend's department and you want to print a document. The old way to do this is, in order to print the document, you have to find a printer in that environment that sits on that network, configure that printer on your machine, okay? Maybe configure the driver for the printer on the machine, and then you print. Okay? That's how you basically print. Right? So that's how the network printer works. Okay? Now, if you have a zero-conf architecture, what would happen is the printers in that environment would post a note on a bulletin board saying, I'm a printer, I'm an HP printer of this model, and this is my IP address. Okay, they'll just post a note. Now, when your laptop arrives in that environment, if you say, I want to print, what your machine is going to do is go to the shared bulletin board and say, is there a printer around, somewhere around here? Okay, so you're going to look for any note of type printer. There may be more than one that you discover. Okay? And then basically all that you will do is you'll pop up a dialog to the user saying, I found 3 printers, pick one. Okay? You just pick the right printer. In this case, along with the note, you can even post the driver if you want to. And then you can basically, a machine can automatically download, configure it and print. So a user doesn't have to go configure any network printer or anything like that. Your machine has gone and found the right device for you. And you just say, I just want to print to this printer, it's near me, and it does it for you. Okay? That's an example of what is referred to as zero configuration, meaning that users don't need to go and keep on configuring printers and all these kinds of things, which is more inconvenience for them. They just want to print. They don't want to spend half an hour trying to figure out how to actually make the network printer work before you can accomplish your task of printing. The system will take care of this for you. Okay? So this is an example of where you would use this kind of scenario. The printer couldn't actually post a note for a specific machine because it did not know which machine might need its services. Okay, the machine that came into the environment wasn't even there when the note was posted. So you can't actually send the message to any specific machine saying, I'm a printer, so I'm letting you know I'm around here. So you just have to post it and wait for someone to come along. So those are all examples of distributed applications which are very loosely coupled. Okay, the messaging is going to be loosely coupled in that you don't send messages to specific entities. You just post them on the bulletin board for later delivery. Okay, is that clear? Any questions on this?
So yes. Does the components have its own memory and the computation is done on the single component, or it's majorly on the data space?
Okay, so you're saying what is in the component. So component is a general name for any application that runs on any machine. So components run on actual computers, clients, servers, whatever they are. The shared data space is also going to be on some machine. It's just a piece of memory. It's like a bulletin board. It's like a physical bulletin board where you go and post notes. It's actually think of it as a simple database where you posted all active notices. Okay? So all the computation is going to be done in the components. Okay? This is simply a data repository of all active notices that have been posted. Okay? That's the way to think about it. There's a question here, yes.
How long will the data be published to the database?
Okay, question is how long will the data be published? So that depends on the application. You can post an expiry message saying this is active for so long. You can say it's perpetually active. That depends on the application. The system is not going to specify any particular expiration times or anything like that. You can decide based on what application you write. As I said, this data space is a simple database. So you can leave the notices there for as long as the application needs to. Okay, so that has to be decided by the application designer. Yes.
And who maintains this shared data space? Is there something like a OS or something that is running?
So who maintains it? So there has to be a distributed system library that going to provide you that functionality. So that's a middleware, because this middleware is going to run on some machine, and that machine is going to maintain the data space. When we actually talk about these systems in a lot more detail, you'll see that the data space itself is going to be distributed. It's not running on a single machine, because then it becomes a central point of failure or there are scalability issues. So it's like a distributed database. So the middleware is going to run on multiple machines. It's like having a bulletin board on each floor of the building. You can go and post to your nearest one and so on. Okay, so all those are actually interesting design issues. We will come back to that later.
This is the difference between this one and the previous one. So the bus line.
Okay, so question is, what's the difference between these two?
Yeah. So I mean, if the bus also keep the data, it's very similar.
Yeah. So question is, if the bus stores the data, is it very similar? So in the event bus architecture, events are not going to persist for long periods of time. Okay? Event gets published. You look at the subscription list. Whoever has subscribed, you deliver. Okay? You may buffer it for short periods of time to account for delays and whatnot, but you're not going to keep it for 6 days. Okay? In the other architecture, the events here that you publish are going to persist. Okay? They are going to stay there for days or weeks at a time. So that's the main difference between the two. So you're not. So it's like if I publish a stock price, somebody comes 6 days later, they are not interested in what happened 6 days back, right? So that's the difference between the two. So events are going to be delivered as soon as they're published or soon after they're published. Okay, is that clear? Any other questions there? Okay, so next architecture, which is what is going to lead to some discussion of multi-tier systems, is the client server. You probably have all heard of the client server architecture, where it's a very common way of designing distributed applications, distributed systems. So you have at least 2 machines, okay? Not always 2, but at least 2. Usually you have more than 2. One called a client, one called a server. Okay? The server is going to provide some sort of a service, okay? And the client is going to send requests for that service. So this is a timeline figure that shows how the client and the server communicate. Okay? So the dark line shows that that entity is executing. The dotted line shows that the entity is waiting. Okay? So in the timeline. So initially you'll see that the client is executing and then decides to send a request to the server. The request comes over a network. It comes to the server, and while the request is being processed, the client is blocked. Is waiting for the response. Is not doing anything, which is why that line is dotted. That's saying waiting for results. In this, when the request reaches the server, it's going to process it. It's going to send back a reply. And once the reply reaches the client, it's going to resume execution. A very standard, what's referred to as synchronous method for client-server communication. Okay, that clear? All right. So now we will look at, when you have a client-server architecture, how do you actually map an application and what parts run at the client, what parts run at the server, and so on. And this is where we'll get into some discussion of multi-tier architecture. So as you will see, if you take this model and an application model, there are 2 things to think about. One is, what are the parts of the application? A typical application is going to have a user interface. Okay? It's going to have the application logic, which is referred to as the processing level, and it's going to have some data which may be stored in a database that the application accesses over the course of its execution. Okay. Now, if you map this, let's say, to a simple web-based store, okay, e-commerce application where you want to sell something online. Okay. In this case, the logic or the code that you write for receiving requests and processing requests, all of that is going to sit on the processing level. Okay, this is the tier at which it sits. Your data level is a database that will have, let's say, a catalog of products that you're offering to sell. Okay, let's say it's a bookstore. Okay, you will have a catalog saying, I have all these books for sale. Users may first search for books. Once they find a book they want to buy, they're going to put it into a shopping cart, and then they're going to go actually process a transaction to make a purchase. Okay, so all of that code to process queries for books or then buy a book, all of that is going to sit in the processing tier, and the catalog and the orders and all of that will actually be stored in the database in the data tier. Okay? And the user interface is simply going to be the web-based interface that you provide to your end user. Okay? Part of that is going to run in the browser, but not all of that is going to run in the browser. Okay? So that's an example, but let's look at this in more detail here. Okay, I'm going to now give you another example of a search engine and try to show you how to map this into a multi-tiered framework as well. Okay. You don't need to know anything about a search engine to understand this. It's very straightforward. Okay, at the very top, you have the user interface. Okay, that's the user interface there. Typical search engines are going to give you a box, text box where you type a keyword and you hit submit. Think of Google, for example. Okay, your interface is running in a browser. It's very straightforward. It's at the top. Okay. So now when that user is going to submit a query, a set of keywords, it's going to actually come to the search engine itself. Okay. And the middle part of the search engine is where all the code for the search engine resides. Okay. So when the set of keywords comes in, those keywords have to be translated into actual queries that you make of whatever data you crawled and you kept in your search engine. Okay. So that is this component here. It's called the query generator. So you get a keyword expression and you translate that into a SQL query, a database query. Okay. Excuse me. So that query is going to go hit your data tier. Your data tier could be an index of all the pages that you have gone and crawled on the web. Okay. You basically go crawl pages, make a copy of it, you store it in your database, and you have an index of it. Okay. So you are going to go take your keyword and figure out what pages match it. Okay. So that's your query is going to go. So this is your data tier. Okay. Now you may get some results back based on what pages are going to match your query. Then you are going to go and give it to a ranking algorithm, which is going to say which are the most relevant pages. There are 10,000 pages that have this keyword in it, but I have to present this in some relevance form. So you're going to give it to your ranking algorithm, which is going to rank order these pages by relevance or whatever metric the search engine has decided for itself. Then you are going to take those results that are reordered and you are going to reconstruct an HTML page out of it. Okay, so basically you take all the results, you construct an HTML page, that's your HTML generator, and that HTML page is going to go back to your end user. Okay, that will be the response that is coming back from the search engine. Is that clear? Okay, there's nothing more you need to know about how any of this works. I'm just trying to point out how you can implement your search engine in a multi-tiered fashion. Okay, so this is one tier. This is a database tier. It's called the data level. This is the application tier, also called the processing level. That's a user interface tier. You'll see that this is a layered approach. Okay, there are only 3 layers here. Okay, each layer is only talking to the layer above and the layer below. There could be more than 3, okay, but typically you will have 3, at least 3. Okay. So this is a standard way of designing any application. I showed you, or not any application, any web-based application. I showed you example of search engine. I also mentioned how this is going to also work for building an e-commerce store, an online store that sells books or whatever else it's selling. Okay. Now what we'll do is take a look at this architecture and map it into a client and a server. Okay. In this case, it should be clear that a user interface typically sits on the client side, and the application tier and the data tier are going to sit on the server side. Okay, so that boundary there is going to be also the client-server boundary, but that doesn't always have to be the case. You will have actually a spectrum of choices of how you go about implementing which of those tiers sit at the client and which of these tiers at the server. Okay. So here are 6 different scenarios. Okay, and this dotted line here that is actually you see here, okay, is the boundary between the client and the server. Okay. Anything above the dotted line is on the client machine. Anything below the dotted line is on the server machine. And each of the scenarios shows one architectural choice of which tier you have decided to put at the client, which tier you have decided to put at the server. Is that understood what I just said? Okay. So in the first case, you will see that the user interface tier is split into two. Some of it is running on the client, some of it is running on the server. The application tier and the database tier are on the server. Okay. This is a pretty standard approach for designing your web-based application where, let's say, your application pages have some JavaScript. Okay. So some of that code is actually running on the browser in using JavaScript. Okay. And based on how the JavaScript is interacting with the server, some parts of the user interface will also run on the server to process any clicks that are coming, any asynchronous requests that are going to the server and so on. So your user interface is not all web-based. Okay? It is going to, a lot of it is going to be on the client end in the browser, but some of it is going to run on the server. And then the application logic and the database is on the server in this case. Okay? This is the first architectural choice. Okay. Here is another one where you put all the user interface on the client. Okay. Nothing, there's no user interface part on the server. So the user interface directly sends a request to the application tier, and the application tier is going to make a request of the database tier and send back results. Okay. That's the second choice. Here's a third choice where you took the application tier, you split it into two. Some parts of the application code is not only the user interface, but some part of the application code is going to actually reside on the client machine and some of it on the server machine. Okay, database still on the server. Okay. Fourth choice is the user tier and app tier is both on the client, only the database is on the server. The last one is where you actually took some of the data is here and some of the data is on the server. So depending on what you are trying to achieve, there is no one answer on which of this is the right approach. It is just a spectrum of choices. And different applications will make different design decisions and fall into one of these 5 or 6 choices that you have. Okay. Now you can think of many examples that you actually encounter and try to think about how they map onto these choices. Okay. So let's take web-based email. Let's take Gmail or Yahoo Mail, and you can think about which of these would it fit into. Okay, so the Gmail or Yahoo Mail, you have client-server mail application. Okay, you're using a browser to access mail. Okay, so then the question is, what parts of the applications are on the client and what parts on the server? Okay, the database is your inbox. Okay, that's your mail itself, so that is clearly on the server side. Okay, so the question is, where are you going to draw the line of where is what is on the client, what's on the server? Which one?
C.
C, okay. Can you explain a little more?
Because we don't have the application logic, but
Okay.
We do have the application.
Okay, so you have to think about what it means. So you could have said C and parts of it, that your answer is probably valid. You have to think about what the application means in some case. And depending on what it means, the answer could be either A or C. Okay? The application is simply what you see in your browser. Okay? Basically, you can compose an email in your browser and send mail and receive mail. Then you're probably somewhere here. Okay? Because you're using JavaScript and so on, you're here. The application and this application is actually a mail application. It's going to be the SMTP and the IMAPs and everything is actually on the server side. That's one way to think about it. Another way to think about it, the application is what is running in the browser. In that case, this is true. Okay? But in the web-based world, the application that the user interface is actually incorporating some of the application parts. Okay? So this is probably a better way to think about it than that. Okay? And the reason to think about it this way is, let's now, instead of webmail, let's say you use a full-fledged mail client. You use Thunderbird, or you use Outlook, or you use Apple Mail client to get mail. Okay. Now you think about what is on the client and what's on the server.
Is the database
Database is on the server. Database is your, let's say, IMAP inbox that is all the mail is actually sitting on the server. Okay, it's actually stored in the database. So that's true.
the last one, because you keep some of the data on your end as well.
Okay, so you can think of those scenarios. Depending on your mail client, you will be actually in this side of the spectrum. Okay, as was pointed out, if you cache your mail, means you can actually, even if your machine is disconnected, your machine has cached some of your mail, you are here because parts of the mail are on your client, parts on the server. There are some mail client that don't cache any mail at all. There you are here. You have a fat client. The client is not a thin web-based browser. It's a full-fledged application. It has application logic. It has the GUI in it. So you are in this side of the spectrum. Okay? Now, depending on whether you consider IMAP to be sort of a server-side application, you can even think of some part of the mail server is also doing the processing. So you could be in one of these three, right, depending on what you consider the application and what you consider the client and the server. Okay, so you have to define what the application means, and depending on that you will see. But clearly you won't be here. Okay? You are actually on this side of the spectrum. Okay? Web-based applications, your clients are running inside a browser. They're more lightweight. Lot more processing is happening on the server side. So you're on this side of the spectrum where some parts of the application are certainly on the server side. If you have fat clients, okay, which means the full-fledged clients, you're on this side of the spectrum. Okay, is that clear? But what you need to keep in mind is, whatever you side of the spectrum you are in, your application, your distributed application has multiple layers or tiers. Okay? And the three common ones are, there's an interface that you expose to the end user. That's how user communicates, not communicates, rather interacts with the application. There's the application code or the logic, and then there's the database. Okay? So those are three common layers in any web-based or distributed application. It doesn't have to be web-based. Okay. All right. So here is a blown-up picture of what I had shown in the client-server world. Okay. But now you actually have three tiers. So because your tiers are talking to one another. Okay. So you will see that you will now have user interface tier. It sends off a request. It comes to the app tier. The app tier is going to process that request. Probably make queries to the database tier. Okay, so these queries are then returned back to the app tier. The app tier is going to process it, construct a response, send it off to the client. Okay, so what I showed you 2 or 3 slides ago as a client server. So this figure, because you have multiple tiers, actually looks like this. Okay, depending on how the interaction takes place. Okay, yes, question.
Can there be scenarios where either the request side of the application or the return side of the application is on the client side and the other side is the other part is on the server?
You are asking the request is on the server?
In the application layer, the part that is requesting from the database, that is on the server, and the return part is on the application, the user interface side, client side.
Okay, so you are saying that is it possible for the database to directly return results to the client, even though the request is coming to the application tier, you make a request and the reply goes back to the user interface?
Part of the application layer is on the server and part of the application layer is on the client.
Yeah, you could have scenarios where part of the application, if you look at this, you will have scenarios where some of it is here, some of it is there. The specific case that you said which short circuits the server side of the application results, well, that depends on what you are trying to achieve. There's nothing that's going to prevent you from writing your code any way you want. Okay, but typically you will have 3 tiers that are involved in processing a request. Okay. In the web-based world, you will have the front tier, okay, on the server side. Okay, so I'm going to draw a picture to make this more clear. Okay, so you have a browser. That's going to send request to a server. Okay. Server is at least going to have 3 components. TP server, app server, and there is going to be a database server. So this is a standard way to write your web-based application. Browsers make requests, they come to an HTTP server. This is an HTTP request. So you need some HTTP server on this side. Okay, HTTP server is going to send this off to the app server. App server could be written in a language like J2EE. If it's Java, it could be written in PHP. If you're writing PHP code, it could be written in Python, Ruby on Rails. There are many different languages you can write this code in. Okay, so that's going to be your app server. Okay. And then the application server is going to talk to some database server. Requests typically involve making queries to the database, getting back some replies, and then the reply comes back, and then the app server is going to process it, construct an HTML page, send it back to the HTTP server. HTTP server is going to send back a request to the browser. Okay, so this is essentially your server. Okay. This is your client in this case. Okay, that's your boundary between the client and the server. This is one way you are going to write your multi-tier web application. We'll see that if, strictly speaking, there are now 4 tiers in this case. Okay? The server side, there are 3 tiers, and there's a client tier. Okay, or some part of the core application running on the client tier. Okay? So if you have heard, so now, although this server has 3 components, how the server components get mapped onto machines is an orthogonal problem. All of these 3 applications can run on one machine. Okay? You could also run them on different machines. Okay? The HTTP server could run on machine A, this could run on machine B, this could run on machine C. Okay? Each of these tiers could be replicated. You could have 10 machines that are all serving application requests as app servers, because this is a big store that has lots and lots of requests, so one machine cannot handle the load. So you might decide that this tier has actually n machines, and it's greater than 1. This tier could also have more than 1 machine, and so can this tier. So there are many different ways by which these components can get mapped onto machine. The simplest case is where all of these components get mapped onto a single machine. Okay, this is often referred to in the Linux world as a LAMP machine. Okay. LAMP is an acronym standing for Linux, Apache, MySQL, PHP, a popular set of applications that are used to write these kinds of applications. So you use only open source, so you use Apache web server, you run your database on MySQL, you write your code in PHP. It's called a LAMP stack. Okay? Single machine. Okay? That's the simplest. Okay? Then you can basically go and say this is going to run on its own machine, this runs on its own machine, this runs. That needs at least 3 machines. Okay? And you can scale arbitrarily. You can start putting more, this is a cluster, this is a cluster, that's a cluster. And you can keep expanding your capacity as and when you need more capacity. Okay, is that clear? So what you will see is designing multi-tier applications and then architecting them on a cluster depends on what is the size of your user base, how many requests do you expect to see, and so on and so forth. It can get very complicated, or it could be as simple as everything is running on one machine. Okay, so broad spectrum of things. Okay, it's nevertheless distributed, because even if all of the server side runs on one machine, there's a client machine and a server machine, at least 2. Okay, so it's still a distributed application. Is that clear? Any questions here? Okay, so I'm going to stop with the client server and move on to the next architecture, which is going to be P2P or peer-to-peer architecture. Okay, so it's a different way of building applications. In the client-server world, there are client machines and there are server machines. Server machines tend to be more powerful. They provide a service that clients access. Okay? Now, in a peer-to-peer world, the distinction is gone. All machines are peer. All machines are equal. Okay? So peers can actually serve as clients to some machines and serve as servers to some other machine. So the role of a peer can be either that of a client or a server or both at any given time, depending on what it's actually doing at any instant. Okay, so you don't say this machine is only a server, this machine is only a client. That's no longer the case. Okay, you basically have interchangeable roles, and this is why machines are now called peers rather than being either labeled a client or a server. Okay. So this is a P2P architecture or a peer-to-peer architecture. There are many scenarios where P2P architectures are used, and I'm going to first talk about some concepts, then we'll talk about some applications. Yeah. So here is what is shown in this picture is one way to design a peer-to-peer application that is called a structured P2P system. Okay. And it is basically using what is referred to as a distributed hash table or a DHT for you to figure out what machines are actually going to store your content that you're trying to access or serve your request that you're trying to send into the system. Okay. And the way this system works as follows. Okay. So assume that a collection of machines has some objects that they are willing to serve to whatever other peers want to access them. Okay. There's a collection of objects. Okay. You take this collection and you partition it into smaller groups, and you assign each group to a machine, saying you are responsible for serving requests for these 3 objects or these n objects. Okay. Another group is assigned to another machine, saying you are responsible for handling any requests that are coming for these objects, and so on. What the objects are doesn't matter at this point. You just have some collection. Okay. So you take this collection, you partition it into groups, you assign each group to one machine. Okay, in this case, one machine, and say each machine is now responsible for serving requests. So now you have partitioned the responsibility of serving requests to all the machines by taking your collection and mapping it into the machines you have in the system. Okay. Now suppose now a request comes in for a certain object I. Okay. You have to now figure out which machine did you assign responsibility for I and send that request to that machine. Okay. Is that clear? You had objects, you gave it to some machines, and each machine is responsible for some subgroup of the objects. Now some peer sends, I want to access object I. How do you know which machine has that object I? Okay. The way you figure that out is using this notion of a distributed hash table. Okay. And the way you are going to figure this out is you are going to maintain a table saying object I, responsible machine is machine K. You are going to maintain this table. Okay. So when an object request comes in, you are going to do a table lookup and say which machine is responsible for this object, and you are going to send that request to that machine. Okay. Now in a distributed hash table, this table itself is going to be distributed. There's no centralized machine that's going to maintain a master list for you. You're not going to have one gigantic table and that is the machine you first ask, say, where is this object? This table itself is distributed, so are the objects. So what is shown here is how your distributed table is mapped onto multiple nodes in the network. Okay. So we will basically arrange we'll number the nodes 0 through n. Okay. You will give a logical ID I to each node, and they are going to arrange themselves into a logical ring. It's not a physical ring, just a logical ring. Okay. And just as you took the objects and you distributed it to nodes, you are also going to take the table. You are going to chop it up into pieces, and each part of the table is going to be given to one machine to manage. Okay. So that's what is shown here, saying node 1 is responsible for tracking which machines are responsible for objects 0 and 1 in the system. And then you see node 4 here has another part of the tables. Okay, rows 2, 3, and 4 of the table are assigned to node 4. Rows 5, 6, 7 of the table are assigned to row 7. Node 7, there's node 12 that is responsible for records 9 through 12. So these are going to be called keys. Okay. This distributed hash table is going to be called a key value store, where the key is the ID of the object and the value is, let's say, the machine that has stored the object. That's your table. Okay, so essentially your table is a key value where you have key, you have value. Okay, so this is going to be object 1. It's a machine I. Okay, object 2. You say this is the machine that is actually has this object. Okay. So you have this table. Okay. What you did is you partitioned this table and you said these rows of the table are going to be assigned to node 1. The next 3 rows are assigned to node 4 and node 7 and node 12 and so on. Okay, is that clear? So when a request comes in for saying where is object I, you are going to essentially inject it into this ring and it's going to propagate until it hits the node that actually has that record in its table, and then you will basically know which machine actually holds that object. You will get back a reply and then you contact that machine and access the object directly. Okay, so you're going to first do a table lookup and then you're actually going to access the object. Okay, is that clear? Any questions over? Yes?
How is the division managed?
Oh, I'll come to all of it. Just one second. So far, so good. Okay, so now we'll see where this peer-to-peer thing comes in. Okay, in a peer-to-peer system, we are going to assume that no peers are going to come and go. Okay, we'll allow dynamics. In other words, unlike a server machine where the machine is up all the time, peers we will not make that assumption. Okay? Peer could be just somebody's laptop that's participating in the system. If you shut the laptop, machine is gone. You know, the disconnect from the network, machine is gone. So peers can come and go. Okay? And we want the system to continue to function even when peers come and go. Okay? So basically, let's say what happens when a peer comes in. Okay? So new node joins your network. So the way it is going to join is it's going to pick an ID for itself. It's randomly going to say, pick an ID that's not yet assigned. Say I'm node 10. Okay? So that's why this node is grayed out because there is no node 10 currently in the system. So new peer comes in, it picks an unused ID, it joins. Like I'm node 10. Because then it says, now that I'm node 10, what can I do in the system? Okay? So what you do is you ask your next neighbor, saying, give me some of your table entries. Okay? Because I'll take over some of what you are doing. So that node is going to say, I am responsible for 5 records. I will take charge of 2 and you take the other 3. We will split the keys and give some of these keys over to node 10. Okay, so now node 10 will take over some of the tasks. Okay. So as the number of peers in the system grows, the job of tracking the table and responding to requests keeps getting distributed across larger and larger number of nodes, and the load actually gets balanced across the network. The reverse has to happen when nodes are going to depart. Okay, if a node suddenly decides to go away, some other node has to take over its responsibility. So if again, let's say same example, if this node 10 disappears, then node 12 has to say, okay, my neighbor is gone. So whatever my neighbor was doing, I have to take over. Okay, so all the entries that it was tracking, it has to take over. Okay, which means it has to keep redundant copy, otherwise the data is going to be lost, but let's not worry about redundancy for now. Okay, so you have to deal with peers coming and going in the system. Okay, next question.
So when a node leaves, do they have to notify their neighbors before they leave, or do their neighbors check to see?
The question is, when a node goes away, do they have to notify their neighbors? It would be nice if they notify the neighbor, but the system shouldn't depend on it. Okay, so basically, you can't assume such. There could be any reason a node leaves. A node may just fail. Okay, the hardware fails or the machine crashes. There's no way to notify because that's not an anticipated departure. Okay, now if let's say I shut down my P2P code that's running, that's a graceful shutdown, maybe you can notify. So you shouldn't depend on it. So it's better to assume that nodes can arbitrarily disappear. Okay, that's like a failure. Okay. So P2P systems are designed for more dynamics, unlike client-server systems. A client-server system, you don't expect that server will randomly disappear and some other server has to magically appear. None of that. You assume that most servers are more stable. Clients you don't care about. The P2P system, we don't make that distinction. We assume that peers can come at any time, peers can leave. When more peers join, you take the responsibility that the current sets of peers were handling, and then you offload some of the work to the newer peer. So there's less work for everyone. When peers disappear, others step in and take over the task. Okay? So in other words, the distributed table that is being maintained there, the way it is split across peers keeps changing depending on how many peers there are in the system. Okay, if you have n rows and k peers, you should basically have n over k entries responsible for each peer. So you basically partition your table into some smaller number of groups, and then each group is assigned to peer. Okay, is that clear? Okay, this is referred to as a structured P2P system. It's also referred to as SCORD. Okay, that's the name of the system that was actually proposed. It's used in many different scenarios. Any questions here? I'm going to show another P2P system next. Okay, so here is a two-dimensional peer-to-peer system. Okay, I'm going to describe it in the abstract first, and then we'll look at a little more detail. Okay, so in the previous case, okay, the keys were simply numbered. Okay, so the keys were one-dimensional. The keys had object 1, object 2, so they're just object IDs that are one-dimensional. They went from 1 through n. all you have to do is, if I need to locate object I just basically go and do a lookup of that entry that tells me which machine has object I, and then I contact that machine. That's what I have to do. Okay. In this system, which is referred to as CAN or Content Addressable Network, keys are two-dimensional in nature. The keys have two attributes, I and J. Okay. What that attribute is doesn't matter from the system's perspective. It could be anything. You could say it is a file name and a file type. The object has a name. It is the name of the file and it's a type. So it could say, you could say, I want a file name foo and it is an image file. I want file name foo and it is a Linux distribution. It's an ISO image. You could basically have a name and a type. In this case, there's only name, there's no type associated with it. But here we have a name and a type, so that's why there are two coordinates or two attributes, I and J. Okay. And the way you look at it is, this is your coordinate space. This is the set of all the keys that could be in the system, all the objects that could be in the system. And each rectangle there is basically the region that you assign to a particular node, saying any entry or any queries with sort of that fall into that region are your responsibility for that peer. Okay. And we have basically assigned numbers rather than strings, but it's the same concept. So we assume the attribute one attribute goes from 0 to 1, the other attribute also goes from 0 to 1. You can think of any string being mapped onto an integer space and basically get this mapping. So what basically happens is when a node comes in the network, it's given a rectangle, just as you got some rows here to manage. Now you get some address space to manage, saying this is your responsibility. Any queries that basically map from 0 to whatever, 0.2 on one attribute and 0 to 0.3 on another attribute is this node's responsibility, and this rectangle is that node's responsibility, and so on. Okay. So when a new node joins, it's going to pick a region for itself, and it's going to split that region from whatever was managing. So here is an example of a node new peer joining the system. Okay. So it basically joins at this location. It picks a coordinate for itself, and it basically takes this rectangle and it's going to split into two. The previous node manages the upper half and the new node manages the lower half. Okay. Just as you took a one-dimensional attribute and you said, okay, then you manage 5 rows, you take the first 2, I'll take the other 3. You're just doing the same thing in two-dimensional space. Okay. Yes.
Would you need to maintain some redundancy in these models?
Yes. The question is, do you need to maintain redundancy? It's the same issue as before, that if a node suddenly disappears, because peers can come and go in any P2P system, whatever entries it was managing in your hash table, it's a two-dimensional hash table, you have to take over. So if you do not have redundancy, you will lose those entries. So either you have to reconstruct them or you have to keep a redundant copy. Okay? This is an abstract concept. It doesn't tell you that should you maintain redundancy, should you go query all the objects and reconstruct the table. Right. That is left to how you implement the system. This is simply saying how is the set of keys mapped onto nodes. When a node comes, what happens? When a node leaves, what happens? Yeah, yes.
And how the regions for partition?
How are the partition? Okay, so partitioning is basically. Erase this. So the question is, how is it partitioned? So initially, let's say you have the entire table, which is a two-dimensional space. There's only one node. It's in the middle here. It manages all the requests that are coming. Okay? Let's say node second peer joins. So now that you are splitting your responsibility between two peers, so you basically say, I'm going to split this in half. Okay? The first node basically is responsible for managing all the requests that map onto this part, and another node manages keys that are in this half. Another node joins. You're going to take one of these two and you're going to split it. Okay, so then one node does this, one node does this. So you keep splitting this. So that's basically what is shown here. After some number of nodes arriving and departing, this is what is going to happen. Okay. Now there are some interesting things here, which is if you want to keep those rectangles, you have to do some additional partitioning when a node departs. Okay, so for example, if this node departs, the previous node can take over and he basically has this big rectangle, comes back again. But let's see what happens if this node departs. There is no easy way to join this rectangle with some other rectangle. So you have to repartition probably this space by saying I'm going to draw a line here and this part and that part joined together, and this part and this part joined together. Okay. Unlike in the previous one-dimensional case, you could just take those keys and give it to some other node and just starts managing multiple rows. In CAN, when your node departs, how to take the responsibility of the node and repartition is a little more complicated. Okay? Is that clear? Any questions here? Yes.
Is there a maximum limit on number of pairs in this?
Is there a maximum limit on the number of pairs? This system is not going to impose any limits. Basically, it depends on what kind of system you are maintaining, how many nodes there are, how many entries there are, and so on. Okay? There are many scenarios where P2P systems are used. Okay? In the early days when these systems became popular, they were used for sharing music files, and there were lots of controversy about it because it was not legal and whatnot. Okay? But those were the early days, and there were lots of music files and lots of users and so on. Now they are used for many different scenarios. So, common example where P2P system uses systems like Skype. Okay, Skype uses a P2P model. The objects that you are trying to look up are actually user entries on user status. Is the user logged in? Is the user offline? And so on. That is what you are maintaining, and the IP address where you are logged in from. If somebody wants to connect to you, they need to know your IP address. So that is what is going to be maintained in your table. Okay, is this user logged in? And if so, what is their IP address? And then there are lots of Skype nodes are themselves responsible for managing this table. Skype doesn't provide additional services. Okay, typically, there are other nodes. Some node in the system is chosen as a peer, and so you manage some entries. Some other node is going to be given some other entries and so on. So when you log in, your list of contacts is going to be queried in the network, and you get status. Okay, because you are basically going to say, is user XYZ logged in, and is going to go into the network and it's going to assign and go to whoever is managing, and that entry is going to tell you if the user is logged in or not. And all the status updates are going to be sent to that node and so on. Okay? Now, just the reason I mentioned this example is Skype is a very large application. There are tens of millions, maybe hundreds of millions of users. There are lots and lots of peers participating. So you have to think of a very large scale system. So there's no real limit. You can scale arbitrarily depending on the size of your application. Any other questions here? Okay, so I'm going to go on and talk a little bit about unstructured file systems or P2P systems and stop there. So here, the two systems I showed you, CAN and COD, are referred to as structured peer-to-peer system. Okay? That is what emerged out of the early days of peer-to-peer systems, which are what were referred to as unstructured. There were many examples of unstructured systems. There's Nutella and Kazaa, and there's a whole set of these systems that were designed. And they are also peer-to-peer system. They use a slightly different model. They didn't have the structured key value stores and anything like that. So what happened in unstructured peer-to-peer system was as follows. Okay, so let's assume that there are some nodes that are already participating in your P2P system. Okay? When a new node joins, and I'm going to use a green node to denote a new node, it has to figure out some neighbors for it. It will randomly say, I'm going to pick two neighbors, which are randomly chosen as this and this. Okay? So you've basically formed those two links, and now this node can talk to these two other nodes, and those nodes are themselves connected to other nodes and so on. So you basically form a network in this fashion. Okay, when yet another node joins, let's say pink node joins, it picks some number of neighbors randomly. It will pick this and let's say that node, okay, and so on. So your network is going to grow in some unstructured form. The topology of the network is no longer structured as a ring or a two-dimensional space. It is arbitrary because nodes are joining the network. They're arbitrarily picking some small subset of nodes as their neighbors and constructing links, and that gives you whatever topology is going to form as a result of this. Okay? Now, in this case, you do no longer have a table that is being maintained. Okay? There are only objects that the nodes are sharing, and the way the system is going to work is if you are interested in object I, you are going to query for that object by what is referred to as flooding. Okay? In flooding, what you do is you say, so let's say this node initiates a query saying, who has object I? Okay, so you say object I. So you send a query to your neighbors. Okay? Your neighbors are going to receive the query, send it to their neighbors. And their neighbors are going to receive that query and send it to their neighbors, and so on. So your query is going to propagate through the entire network. Okay? This is referred to as flooding. So you flood the network by asking everyone in the network, do you have this object? And then eventually replies are going to trickle back. Okay, whoever has it is going to send back yes messages, and then you're going to get a list of any nodes that actually have the object. Okay?
What if you're searching an unconnected network?
What if you have an unconnected network? If the network gets disconnected, you can't reach the other half. Of course, you'll have two peer-to-peer networks at that point. Okay, so the assumption is you have a connected network. The network disconnects, or some part of the network disconnects, then those nodes can't talk to the other side. Okay, so this is referred to as doing lookup by flooding, as opposed to having a structured table where everything is maintained for you. Only go look up the table. Here you don't maintain any metadata, no directory table. You just ask everyone. Okay? This may can be enormously wasteful because every query may come to you, even though you don't have those objects. You'll have to keep saying no to lots of queries, even though because it's been flooded, you're going to get all these queries. Okay, so you'll use a lot more network bandwidth than you would have in the structured case, okay, where you make more directed queries and they only go to the nodes that may eventually have the object or the information about who has the object. Okay. So this is referred to as unstructured networks. Yes, question.
So if there is a cycle, is it impact the performance of flooding?
There's a good question. The question is, when you flood, if there's a cycle, there will of course be lots of cycles. If flood, then you don't want messages to circulate forever, right? So you may have a scenario where you have this topology. This message goes this way, it comes here, and if it comes back here, you have a cycle. So there are going to be cycles in this graph, but the way you are going to prevent messages from circulating forever is that when a message goes by and a query goes by, you will keep track of it in a table for some period of time. Right? If the query cycles back and comes to you again, you will see that I already saw this, I'm going to drop it. I'm not going to forward it and just have it keep cycling forever. Right? So you'll keep track of what queries have gone by. If because of the cycle it comes back to you, at that point you will drop it. Okay? So essentially you are not going to have messages that are going to sit in infinite loops here. Okay? But that you have to prevent from happening. Any other questions here? Okay, so I'm going to, yes, your question.
Can we decide on number of hops the object can
Yes, so the other question is, can you decide on the other number of hops? When you send a query here, you can also assign a hop count that says flooded, but flooded only to up to n hops. Let's say you pick 7 hops. That means it's only going to go to nodes that are 7 hops from me, not forever. Because if it's a large network, you don't want queries from going all the way through entire network. You can say, I'm going to restrict my query distance to n hops. You can pick n. I just picked 7 as an example. That is going to also prevent you from wasting resources because your object is with a very small number of nodes. If you have to ask 1 million nodes which of the one machine actually has your object, that's enormously wasteful. Okay, so you would want to restrict your query to a certain subset of your network, not the whole network. That is typically done by adding a hop count. Hop count basically gets decremented every time a node receives it. When it reaches 0, you don't forward it anymore. You said that this message has reached the boundary of where it needs to go. I'm not going to send it any further. Okay? So you can use these kinds of heuristics to reduce the network bandwidth that is used. Okay? All right, so we ran out of time. We'll continue this next time. I'm going to stop here for today.